Thank you, Kate, and thank you to the committee for organising such an incredible conference, with an amazing lineup of speakers. The first on the bill is Professor David Griggs. Now, Professor David Griggs has been working in the science of climate change for more than 30 years. His past roles include Deputy Chief of Britain's Bureau of Meteorology, Director of the Hadley Centre for Climate Change, and Head of the IPCC Scientific Assessment Unit. He moved to Australia in 2007 to become the Director of the Monash Sustainability Unit and also the CEO of Climate Works Australia. Not to mention, he's also a member of a number of science and climate change initiatives. So can I invite Professor David Griggs to discuss climate change and sustainability challenges?
Thank you very much. So I've got about 20 minutes, and first of all, I need to congratulate all of you for getting up so early on a Saturday morning. I thought I was going to be speaking to an empty lecture theatre. It's very reassuring to find that there is actually someone here to listen. I've been asked to really just set the scene and talk a bit about some of the basic science. So a lot of you who have been in this field already will be very familiar with this, but maybe some of you aren't. So I apologise if this is all old news to you. So when we start to think about climate change, the first thing to think about is the climate changing. So that's the first thing to look at. I'm going to run a short video which shows the temperature of the Earth from around about 1950 through to the present day. And the bluer it is, obviously the colder it is, and the redder it is, the hotter it is. And I'll leave you to make up your own mind as to whether we've seen any warming over the last 50 years or so. So as you can see, the pulsing in and out of red and blue, that's the natural changes that we see within the climate system, what we call natural climate variability. We get hot years and cold years, wet years and dry years. But I think you can see, and I'll run that through again because it only takes a few seconds. I think you can see that, over that period, there is no doubt that the world has warmed. So we haven't seen a halting of warming. And the world has just continued to get warmer. I mean, if you express that in terms of graphical, then the top left-hand panel here shows the average temperature of the Earth averaged over land and sea. Each one of those points on the graph shows the average temperature that year. And what you can see is that we've seen a temperature increase of about 0.8, 0.85 degrees Celsius since the beginning of the 20th century. If you average that decade by decade, that's the lower panel, and you can see that over the last 4 decades, we've seen a very steady and rapid increase on decadal temperature increases across the world. So since the 1850s, since the 1950s, many of these observed changes have been unprecedented. The atmosphere and the oceans have warmed, the amount of snow and ice has decreased, and we'll go into and look at those in a little bit more detail. But what the Intergovernmental Panel on Climate Change said is the warming of the climate system is unequivocal. Now, they use that word very carefully, and scientists hate using the word unequivocal because that means 100%. The IPCC, the Intergovernmental Panel on Climate Change, uses agreed words for what they mean. So if they say something's very likely, it's 90 to 95. Extremely likely is 95 to 99. Virtually certain is 99 to 100. So if they say unequivocal, they mean unequivocal. So, the temperature increases are not the only changes that we've seen in the climate system. If we see the temperature increase, we would have expected to see other changes in the climate, and we have. So this shows the oceans. In the top left-hand plot, we can see global ocean heat content. As the heat in the atmosphere builds up, the oceans have a huge capacity to absorb that heat. And so sure enough, when we started to measure ocean heat content, we see a rapid increase in the heat in the upper layers of the oceans. If the temperatures are increasing, we would expect to see sea level rising. There are several reasons for that. The 2 main reasons are ice that's on the land in glaciers and ice sheets melts and flows into the oceans. But the main reason is that as water gets warmer, it expands, and so through thermal expansion, it just expands and the sea levels rise. And as you can see in the bottom left-hand plot, we've seen a steady and increasing rate of sea level rise since the beginning of the 20th century. So it's virtually certain that the upper ocean has warmed from 1971 to 2010. The rate of sea level rise since the mid-19th century has been larger than the mean rate over the last 2,000 years. And over 1901 to 2010, global sea level rose by about 19 centimeters. We see changes in snow and ice as well. If you look at the top left-hand plot, that's changes in snow and ice covering the northern hemisphere. Most of the snow and ice on the planet is in the northern hemisphere because of those large land masses. And so what you can see is about a 40% reduction in snow and ice since the 1960s. At the bottom left-hand panel there shows the Arctic summer sea ice extent. Arctic summer sea ice is just floats on the ocean. There is no land at the North Pole. So the ice just floats on the ocean. And every year during the northern hemisphere winter, that ice grows. And every year during the northern hemisphere summer, that ice melts. And the area of that ice at the North Pole has been gradually getting smaller and smaller. And you can see the shape of that curve where it's been dropping off at an increasingly rapid rate, so that now the extent of that summer sea ice extent, around about September each year, which is the end of the northern hemisphere summer, is only about 50% of what it used to be and what it should be. And that caused people to, in fact, our group was the first one to make a prediction that the Arctic sea ice would disappear by the end of this century. And we were attacked by everybody, by fellow scientists, by skeptics, in the media and so on, because nobody could conceive of a world with no ice at the North Pole. Now, I think that's just widely accepted. The argument now is not if, but when. Is it by 2050? Is it by 2070? Is it by the end of the century? So it's not a question of if, it's a question of when. Oh, and I should say, of course, we define what we mean by ice-free as well. We mean less than 10%, because there'll always be a few icebergs floating around. So in 2050, when the skeptics are saying, you said there'd be no ice, and look, here's an iceberg, remember what I said, that we said less than 10%. So, other changes in the oceans. When carbon dioxide, greenhouse gases, go into the atmosphere, some of that carbon dioxide is absorbed by the oceans. So if you look at the top graph there, the blue curves, we can see that this carbon dioxide concentrations in the upper layers of the ocean have been increasing. There's an implication to that. Carbon dioxide, when it goes into the ocean, forms carbonic acid. Carbonic acid, of course, changes the pH of the ocean. And what you can see in the green curves there is that we've seen a reduction in pH. In other words, the oceans are becoming more acidic. So the ocean has absorbed about 30% of the emitted, human-emitted carbon dioxide, causing ocean acidification. And the atmospheric concentrations of carbon dioxide, methane, and nitrous oxide have increased to levels that are unprecedented in at least the last 800,000 years. I mean, that's as far back as we can go. It's probably a lot longer than that. So that's a sort of 5-minute potted, that's the latest science. All of those graphs come from the latest Intergovernmental Panel on Climate Change report that came out in September last year, their 5th assessment report. So what's causing it? Well, we think we know what's causing it, the greenhouse effect. The greenhouse effect is not complicated. All of the Earth's energy comes from the sun. That energy from the sun passes through the atmosphere largely unchecked. Some of it bounces back off clouds, but most of it passes through the atmosphere as so-called shortwave radiation, or ultraviolet radiation, and visible. It goes through the atmosphere, heats the surface of the Earth. That's what keeps the Earth warm. If the Earth then didn't do anything with that, the Earth would just get hotter and hotter. So what the Earth does is re-radiate that energy back out to space to keep the temperature of the Earth at a nice, comfortable temperature. And it does that at so-called long-wave or infrared radiation. And the key about that is that there are certain gases in the atmosphere that absorb radiation at those wavelengths. That's a well-known fact. So, logically, if we increase the concentration of those gases in the atmosphere, we would expect more of that outgoing radiation to be absorbed, and we would expect warming. People think climate change is a new thing. Fourier in 1827 was the first one to figure this out. So, it's been around for a while. So he outlined the principle of the greenhouse effect. He probably couldn't measure it at that time. But John Tyndall in 1881 was the first one to demonstrate this experimentally, how carbon dioxide traps heat of the radiation at that wavelength. And then Svante Arrhenius, the Swedish scientist in 1896, predicted that a doubling of carbon dioxide in the atmosphere would lead to a 5-degree warming. And that's not too far away from what we predict today. And he didn't have any supercomputers and so on to make his predictions. I would take issue with him about one thing, being Swedish and being not very happy about the Swedish winters being rather cold. He actually encouraged us to burn more fossil fuels because it would make the Swedish winters more comfortable. So he got the science right, but I think the interpretation left a little bit to be desired. So, if it's global warming, we should be looking at greenhouse gas emissions. I've just chosen carbon dioxide here. You know, it's easy to see, isn't it? It just keeps increasing and increasing. So the human influence on the climate system is clear. We know that increase in carbon dioxide concentrations comes from burning of fossil fuels by human beings because we can look at the isotopes of that carbon dioxide. And there are several other reasons. So it's extremely likely. Remember that term, extremely likely? That means 99 to 100% certain that the human influence has been the dominant cause of the observed warming since the mid-20th century. Sorry, 95 to 100% is extremely likely. So why are all these people saying that climate change is a load of rubbish? And other slightly less polite words than that. So I'm going to go through a few of the skeptics' arguments and say why I don't believe them, and then I'll leave you to make up your own mind. The first one is climate change is natural. Climate has always changed in the past. It's a natural process. What we're seeing at the moment is just natural. And that's nice because it's half true. Yes, climate has always changed. It changes from day to day, week to week, month to month, year to year. I've talked about natural climate variability. And what we see here is the temperature in the red curve over the last 400,000 years, and that's the Ice Age cycle. That's a natural cycle called the Milankovitch cycles, as the way the Earth precesses around the sun. But if we start to look at that now, and the red on the end is what we've seen over the last 100 years, then we're taking the Earth way outside this natural, what we call these natural guardrails, the natural variability that we expect to see. And if we're going to look at the carbon dioxide concentrations over the next 100 years, that thing would be off the top of the screen. So we're taking things far quicker and far greater than any natural variability. I particularly like this one. I've taken this graph from a climate denier's website, and it shows here medieval warm period. Yes, this drawing of a graph in the IPCC's 1990 report shows it clearly. Now, there are a few clues there. It says a drawing of a graph, which is a bit of a clue. But what you see here is under the medieval warm period, Vikings colonized Greenland, and look how warm it is. The little ice age in around about the 1600s where the Thames froze over each year, and the temperature today on the right-hand side, considerably less than what it was in the medieval warm period. So if the temperature was warmer 1,000 years ago, we weren't emitting much greenhouse gas then what have we got to worry about? So what I've done here is I've plotted all of the attempts of the scientific community to reproduce the temperatures of the last 1,000 years on one graph. So we do that using what we call Paleoclimate or proxy data, because obviously we didn't have thermometers 1,000 years ago. So we use tree rings, ice cores, lake sediments, corals, and so on to try and reconstruct the temperatures. And what you see there is that under most of these, first of all, you see that it's really hard, so there's lots of variability. The second thing you see is that one or two of them do have a spike in around about that medieval period. And those that were ones that were taking data around that area in Greenland. So we know that area of Greenland was particularly warm around about that time, but it wasn't global. And what you see is that in the drawing of the graph, they conveniently left off the last 100 years or so, where we've seen the rapid increase in temperatures. So the temperatures we have today are higher than anything we've seen over at least the last 1,200 years that we've had these, this data. This one I think is my favorite because it uses data that I helped to produce. And they got it right. The pink curve here shows the global surface temperature from the Hadley Centre, from when I was director of the Hadley Centre, so I should know whether this is right. And it is. And you can see on the left-hand side, the temperature plot starts at 0.6 and it finishes at 0.2, so that we've seen a cooling of 0.4 degrees. The green curve shows that carbon dioxide has been increasing, so if temperature's been going down and carbon dioxide's been going up, carbon dioxide can't be causing temperature increase. Well, so this is the actual temperature curve. So what they've done here is they've taken this point here, that really high one, and that little low point there, because if you look at this, It says 1998 to 2008. So why did they choose 1998 to 2008? Because then they could just plot that bit there. And as people with a science background, you know you can't cherry pick data. You just cannot do that. You cannot choose your data to select, to give you the answer that you want. This one, I apologize for the quality of this, because the only place I've seen this is published is in a magazine. It shows sunspot activity and temperature. If sunspot activity and temperature match, sunspots must be causing global warming. This actually, again, they've left off all of the last 30 years when the temperature's been increasing and actually solar activity's been going down. So solar activity is not the one causing it. So that's a few of the skeptics' arguments. What you want to know is what's going to happen in the future. So you can see the year stepping forward here. You can see the temperature scale along the bottom. -2 is blue, +15 is black. That gives a bit of a clue which way it's going to go. And you can see, again, the natural variability. You can see blues and oranges and things as it goes around. And of course, I've just told you that the amount of warming that we're going to see over the next 100 years is dependent on how much greenhouse gas we're going to put into the atmosphere. And we don't know that, of course. So what we do is we develop scenarios, and you'll see here this one's called the A1B scenario, because we love our acronyms. And this is a scenario where the world continues to emit greenhouse gases, but not quite at the same rate as we are today. So it's sort of a medium-low scenario. You could call it an educated guess, if you like. So we assume what population is going to do, what technology is going to develop. And now, as you see, we move towards the present day. If you start to look near the top, you'll start to see more orange appear and less blue. And that's because the major land continent areas of the Northern Hemisphere start to warm up, and even Australia here as it goes around, as we move into the future. And that's because the land areas warm up more than the oceans. The oceans have this huge capacity to absorb the heat. As we get towards the middle of the century, all of the land areas are now warming. The oceans are starting to warm a little bit as well. You still see the occasional blue bit. So there'll still be someone saying, well, look, it was really cold in Nepal this year, so global warming can't be happening, even in the 2070s. Well, you see, there was a blue bit there, you see. So, global warming can't possibly be happening. As we get towards the end of the century, all of the land areas are significantly warm. The oceans have also started to warm significantly. That's about a global warming of about 3 to 3.5 degrees, but significantly more than that, obviously, in the land areas. I used to show a high emissions scenario, but everything went black and people used to freak out, so I don't show that one anymore. This is a nice medium-low scenario, so it's kind of a little bit more sensible. Huge impacts, which I don't really have time to go into. Tim Flannery later in the day will be going into the impacts. What does this mean for people? This shows European heat temperatures in 2003. That 40,000 people died due to heat stress. If you're medical students, that's your future. 1 in a 1,000-year summer, if that was a natural event. 1 in a 200-year summer, even in 2003, with the global warming we'd seen by that time. By the 2040s, a normal summer. By the 2060s, a record cold summer. So get used to it. Biodiversity, as I say, Tim will cover this in more detail. There's a natural rate at which species come into existence and go out of existence. For mammals, 1 species per 1,000 every 1,000 years. We're already at a rate of 1,000 times that rate. We're in the 6th great mass extinction of species. We're losing species today at a rate quicker than we have in any known history of this planet. That's not only due to climate change, that's due to land use change, invasive species, lack of land, conversion of land to agriculture and so on. But climate change is going to increase that by a further factor of 10 by 2100, so to a rate 10,000 times. It's very difficult to estimate what that means in terms of the number of the world's species, because we don't actually know how many species there are in the world. But estimates are something in the range of 20 to 40% of world species will be extinct by 2100. And then finally, so what do we have to do about it? The world's governments have said that they want to limit global warming to 2 degrees. That's an arbitrary figure, but let's just assume that's what you want to do. If we don't have reduced our emissions. The red curve there is what we're going to see. To achieve the blue there, if you look on the top curve, emissions, in other words, how much we put into the atmosphere, has to peak and go down to a very small proportion of what we use today by 2050, about 80 to 95% below today's levels. If we continue to increase emissions on its current trajectory, that's the climate change that we see. And a colleague of mine did something quite nice to this slide, which I've copied. So the first thing you do is put yourself on this slide. And that's really scary, because the first thing you have to do is assume when you're going to die. So the temptation is to run this line all the way out here somewhere. But being a good scientist, I chose the average life expectancy, and let's hope we get there. So that's the climate change I can expect to see in my lifetime, is from sort of, from here to here. What about my children? My kids were born in the 1980s. Same thing there. The climate change they can expect to see in their lifetime is hugely greater than the climate change I can expect to see in my lifetime. And then finally, I've put this on. Now, look, my kids are, in their mid to late 20s now. I don't have grandchildren. These are hypothetical grandchildren. And I've always, when I show this, I always say, it's fine because my kids will never see this. And if they did, they'd completely freak out. But there's a slight problem. My daughter's sitting over there. So I am in big trouble. But should they ever produce grandchildren, the climate change they could expect to see in their lifetime is from there to there, and that's why we need to do something about climate change. And I'm happy to take questions.
Thank you, David. So we'll open it up to the floor to see if we have any questions. Up the back. Someone has a microphone.
Can everyone hear me?
Oh, we can now.
Thanks for the talk. Great talk. The question I've got is about solar activity, because we hear more about greenhouse gas emissions, etc., than solar activity. And I've heard some discussion recently about the fact that we're heading into a grand solar minimum, which could reduce solar activity and could mitigate climate change, certainly not reverse it, and then could sort of lead to a relative increase when it ends. What are your comments on that?
Changes in the sun's output, solar activity, does affect the world's climate. I say affects all the world's climate because it's all down to solar activity. But the variations in solar activity also are measurable in the climate record. They are a relatively small factor. So there's a natural 11-year solar cycle, and then there's a larger solar cycle on top of that, which is the one that you're talking about. In terms of comparing the magnitude of that to the magnitude of global warming, it's of the order of 5%. So it has the potential to mitigate a very small proportion of what we're likely to see, but in no way is it going to get us out of this mess. The microphone is coming.
Could you just make a brief comment about the proposed scientific solutions to this, such as sending particulate matter into the atmosphere, foil reflectors, all those sort of things? Is there anything that you've seen that A, has any merit, and if not, why not? So that's really, we group all of those under the term geoengineering. So, and in fact, what we're doing in terms of putting greenhouse gases into the atmosphere is geoengineering. We are engineering the world's climate. So the question is, can we engineer it back again? And there are several ideas about how we might do that. We can throw iron filings into the ocean, because the ocean is currently undersaturated with respect to iron. Plankton can feed off that. As the plankton grow, they can absorb carbon dioxide out of the atmosphere. We can put sulfate particles or other particles up into the atmosphere which reflect incoming solar radiation. We can put big reflectors in space and all of those things.
Scientifically, all of those things have a logic to them. The thing I would say is that we don't understand the consequences of those things well enough to be able to contemplate them at the moment. We should continue to do research to try and find out if there is anything like that that would help. But, I mean, let's face it, all of our experiments so far in geoengineering haven't turned out too well. People have said, okay, if we put the sulfate particles up in the atmosphere, that will cool the atmosphere. Yeah, but it'll also turn the sky yellow. Oh, yeah, I hadn't thought of that. So there are huge consequences to these things. If you put huge reflectors up, the changes in the wind patterns, the changes in the ocean currents and so on, we just don't know. I mean, we'd be taking a huge gamble. I mean, what is actually more worrying is that there is no political system that governs this. So there is nothing to stop any country or even any individual going up there and just doing it at the moment. And that's what scares me the most.
We've got time for one more question.
We've got one now.
Thank you for that talk. My question, I guess, is more a continuation of the last one. In terms of geotechnology, I feel like that's just putting a Band-Aid over the problem. And I'd just like to know your comments about the alternatives to reducing emissions, or what you could have proposed to do that in each political system to lower a country's emissions.
Okay, now you're getting away from science and into politics, so, but I'll answer it anyway. I'll answer it in the politically correct way first. The atmosphere doesn't care how we reduce greenhouse gas emissions. There's only one way to solve this, and that's to stop putting greenhouse gas emissions into the atmosphere. Simple. The problem is we put greenhouse gas emissions into the atmosphere with everything we do. Every time you turn on a light, every time you get in your car, every time you buy food at the supermarket, it's all got a greenhouse gas emission implication. The only way to solve climate change is to reduce those greenhouse gas emissions. So all of the policies, whether it's a direct action policy or a carbon trading policy or any policy you like, the atmosphere doesn't care. So long as the greenhouse gas emissions get reduced, that's what's needed. But as I say, the magnitude is the thing. The atmosphere also tells you how much you need to reduce it by. That graph tells you how much you need to reduce it by. 25 to 40% by 2020, 80 to 95% by 2050. There's a bipartisan target here in Australia currently of 5% by 2020. If you add up all of the domestic commitments by all the world's governments at the moment, they don't add up to 25% to 40% by 2020. They don't add up to 80 to 95% by 2050. So it's not a political statement to say we need to do more. It's a scientific statement to say we need to do more.
Just one more question from Kingsley.
As a scientist, as you know, the direct action plan of the current short-term federal government is that they will put a lot of emphasis on carbon sequestration. What is your opinion about it in terms of soil sequestration in particular?
Yeah, well, you can ask the Minister later today. I have talked to him about this on a number of occasions. Soil sequestration is, or carbon sequestration, if you like, is can we suck carbon out of the atmosphere through planting of trees and so on. So trees are made of carbon. As trees grow, they absorb carbon, so that's good. But when you cut the tree down, if it rots or burns, then the carbon goes straight back out again. So it's not a permanent solution. You can also do it under the ground. Trees also have roots, which are also made of carbon. And you can also, there are methods where you can enhance the carbon in soils. The difficulty with that is, yes, it's really good, and yes, it helps in terms of the permanency issue to some extent, but there are large uncertainties. If you put the carbon down there in the soil, does it stay there? If it stays there, how long does it stay there? So You know, it has to stay there forever if it's going to solve global warming. It's no good to put it down there and say, well, it's okay for 5 years. You know, there's chemical activity, there's microbial activity. The uncertainties at the moment are large. So yes, there is potential for both sequestration through planting and through enhancing carbon within soil, but there are scientific uncertainties that have to be taken into account.
Right, on behalf of DEA and everyone here, I'd like to thank you, David, for giving a great presentation.
Okay, thank you very much.